Okay. So, I don't know where Professor Vitaletti left you, but I will take it from here. So, and probably you have already seen a few of the things I'm about to show you now about Tf-Idf scoring and so on. Yeah, but we are going to go over this again fast, and then we are going to proceed with the next part. So I guess no recap. That's what we want to do. Right? So I guess you have been seeing what it means to have documents represented in a vector space, right? So far you have seen mostly Boolean retrieval. Then you started looking at weighing documents with scores that reflect how related they are to a query. That's what we want to do. I mean, when you return some documents from a collection, you want to return the documents that are most relevant for the query. Okay? So we have to measure relevance for the query in some way. Now, I think what you have seen with Vitaletti is that the first way of measuring relevance, which was actually the one taken by textual search engines up to some time ago, was simply measuring how similar the text of a document is to the query you are submitting. In order to do so, you need two things. You need to represent both the document and the query in the same space, a metric space, so that you can measure the distance between the query and the document, right? Or the similarity, if you want. It's just two different sides of the same coin. Now, there is the issue is that another issue for going beyond Boolean retrieval is that very often you don't want to have users write Boolean queries. I mean, you can do it. Even on Google, you can write Boolean queries using and or. For example, you want to have a certain pair of words appearing both in the documents. If you don't give any preference, then let's say weighing of the document, scoring of the document will be done based on text and some other measure or document's relevance that we will see later on. Now, blah, blah, blah. This was another thing that you may have seen is this. Yeah, this is very nice for a lot of things, not for this thing. Okay? Just. So that's where we want to start from. Actually, this is what you have. So you have now seen how you can represent a dictionary of terms, each dictionary with its posting list, and this is the minimum amount of information you will find in a dictionary. So for every possible term, you will see how frequent the term is in every document of the collection, where by frequency we mean number of times, number of occurrences. And with this, what could you do? Well, you can do a lot of things. You have seen that you can, for example, try and compute a measure of similarity between a query and a document. How? Have you seen how you're going to do this? Huh? Yes? Cosine similarity, for example. And do you know why cosine similarity and not something else, such as Euclidean distance?
Because Euclidean distance can be arbitrarily bigger.
Good. And have you an idea when Euclidean distance and cosine similarity are equivalent? So they provide the same type of information? No, orthogonal. Okay, you have not seen. Fine, we'll see this. So what you're using is essentially the bag of words. When you have a vector, this is the vectorial representation of the document. So essentially, you have an array, you have a high dimensional space. It's high because the number of dimensions is the number of potential words. And for every document, you have a representation as a vector in that space. right? So you either put the frequency of the words or the terms in each document, or you put some function of it. And I think you have seen that you put something, yeah, more like this, right? For every document, you will actually have a weight for each term that is going to grow like this. This means diminishing returns. So if a word appears one time in a document, fine, you weight it in some way. If it appears 10 times, it is not 10 times more important. It is, you have to smooth. Linear is too much. Okay? So that is how TF pops up. People have been tweaking a little bit with frequencies, and then they have seen that actually using TF you can get a decent performances. But then there is another issue coming into the picture, which is the following. Well, that's fine, but sometimes I have words that perhaps will appear a few times in a document, but still they could reveal a lot of information about the document, right? And for example, I don't know, arachnophobia, right? It is not very frequent as a word, but it's very important if you find it in a word, because probably it's something related to spiders there and the fear of spiders, right? So how do you measure this? So the fact that when a word is rare, its contribution to a document might be very important. You use something called this, inverse document frequency, right? And again, you smooth it. So you don't just take the inverse of the frequency, you take a logarithmic function of it. Once you have these two ways, these two contributions to the weight of a document, of a term in a document, then you can combine them in many ways. For example, if you want to decide what should I put if I have a document represented as a vector. So this is the document, and this is a term. What should appear here? So implicitly, you put either this or something else. When you put this, or also written this way, Tf-Idf, what does it mean? That you take the term frequency in logarithmic form, for example, or if you want, the basic count, and you multiply it by the inverse document frequency, right? Also, so this depends on both the term and the document. This only depends on the term and the document collection. I mean, this depends on the term and all the documents in the collection. And then you can do, I mean, I am assuming you have already gone over this stuff. You just please stop me if I am introducing something new that you have not seen already, okay? So, well, I guess at this point you have an idea of what is the effect of IDF, inverse document frequency. And actually it can be really important. It was introduced for a reason. And that's actually the reason. It really provides valuable information. Yeah, if I give you this, let's call it this in these two terms, and these are the basic statistics about these two terms, which is a better search term? So which is going to get a higher weight?
Insurance.
Insurance would get a higher weight.
Insurance, right? Because the document frequency is lower. And this is the final weighing scheme. Of course, there is a number of alternative schemes that you can find. For example, sometimes, especially when you want to weight a document, a term with respect to a document, very often, I mean, in some application at least, it may be beneficial to consider the standard frequency rather than the log, but then multiplying by the inverse document frequency taken with the log, okay? I mean, you can have combinations. Very often instead, when you have to weigh the queries, the terms appearing in the query, very often you will take this very formula. There is, I do not have to say that, there is some empirical evidence supporting this type of things. They are not really, if you want to really support them with theoretical evidence, you will have to resort to some model of how the documents are generated, right? Normally this is the result of empirical evidence. And then finally, this was the formula used to score a document with respect to a query. Just the sum for all terms appearing in the query of the weights of those terms in the document. That's it. So, and this essentially is what you're interested in. This would correspond to sort of a plain cosine similarity. I mean, it would be the inner product, assuming that one term appears in the query only once. I guess you've gone over this. Vectorial. Okay. So, we were saying this. Before we proceed, I would like to say something about this once more. So, don't you find it a bit strange that two measures that make sense, both of them, cosine similarity makes sense. Euclidean distance in principle makes sense, but then we have seen that it could not be that good, right? For example, there is the standard metaphor used in the following. You take a document, you take the text of the document, you copy-paste. Actually, that's the same document, so you would like it to have similarity 1 with itself, but if you apply Euclidean distance, it is 1/2 essentially. I mean, the similarity has dropped, right? Or if you want, the distance has doubled. That's bad. So, Euclidean distance has no hope at all? Actually, no. If you normalize the weights, Euclidean distance and cosine similarity are giving you exactly the same information. Actually, cosine similarity is just a way of, well, first of all, it's a similarity and not a distance, but you can define a Euclidean distance anyway. But cosine similarity is just a way of using Euclidean distance on normalized vectors. Shall we see why? So, do you know why? So it is, what I'm saying is the following, that if you use cosine similarity and if you use Euclidean distance, they are providing you with the same information. Why?
The distribution of terms is same. The distribution of terms is determined.
You can raise your voice a little bit.
The distribution of terms are same.
Let's consider this case, okay? So let's say these two vectors are normalized. So it means they both have unit length. Now, I take the cosine similarity. What does it mean? Essentially, it means that I'm taking the length of this, well, with sine, but I'm taking the length of this segment, right? Or actually this segment, they are the same. What am I taking with Euclidean distance? With Euclidean distance, I'm taking the length of that segment. Okay? So apparently I'm taking two different things. But actually, they provide the same information. Can you prove that? I'm not proving it now, but perhaps in the second half, I leave you the time to think about. Okay?
The length of H is 1, so the distance of between these two vectors is equal to the angle, the cosine.
Yes, that's you got the point essentially. What your colleague is saying, these two vectors have the same length, so increasing actually this, that's a nice graphical proof of it. So increasing the segment essentially means increasing the size of the angle between the two, and the size of the angle means a smaller cosine similarity, right? Of course, you have to account for the signs and so on, but that makes sense. Can you prove it formally? Not now. Just give it a thought. In the second part of the lecture, we're going to see this. And that's the idea behind. Okay, I guess you went over this stuff again. Can you stop me when we reach the limit of what Vitaletti has said? We should almost be there. Yeah, you went over this example, right? Good. Did you go over this? Huh? You seem doubtful. Okay, we'll go over this. Now, the question is, what shall I do in practice? What is the algorithm to compute the similarity, the cosine similarity between a query and a document collection? Huh? Let's see at one algorithm. So essentially, I guess this is the very same algorithm you have been looking at since the beginning of this course. I mean, it's always the same algorithm, slightly changed from time to time. So in this case, when you were using this to do Boolean query, to answer Boolean queries, and let's say you were taking the end of the terms appearing in the query, this was just the merge algorithm, right? So for every term, you would consider, so you would start with a posting list corresponding to the first term, then you will end it with a posting list corresponding to the second term by running a merge, and so on and so forth for every term until you were finished, right? So actually here you are not doing something very different. Again, if you assume that the documents are sorted in every posting list by doc ID, what you are doing is, for every term, go to the next document and add it to the weight. So you do this for each query term. So it means for every posting list, you update the weight of every term. Okay? How are you going to do that? So what is the weight of a term? When you apply cosine similarity, what is the weight of a term? The cosine similarity between a document and a query is just the inner product, right? I mean, normalized, of course, by the length. That's fine. But it is the inner product. So let's say that Q is a query represented as a vector, and D is a document. This is what I'm taking. Actually, I prefer it written like this. That's just my personal taste. Okay? Yeah? Do you recognize this? The sum of the weights of the terms in the query. This is the weight of the ith term in the query. This is the weight of the ith term in the document. However you want to compute them, okay? This is the 2 norm. It's just a compact way of writing the inner product. So this is the cosine similarity, correct? I mean, the cosine. The higher the cosine, the happier we are. Good. Now, if you look at this, so we can make a couple of observations. The first observation is the following. This term, this is common. So remember what is your task. Your task is finding the documents that have the largest cosine, the largest cosine with the query, right? Yes, you remember? But this term in the numerator, in the denominator, is always the same, correct? For every document. So we don't need to consider this. We want to rank the documents. We do not want to have the exact scores. You see my point? So I would just want to decide if document D1 is closer than document D2 to the query. I don't want to know how much is the cosine between document D1 and D2 with the query, right? So actually this I can forget about. This I will have to keep. Then the inner product. So the inner product, what is it? Well, that's very simple. It's just Qi di. So where Qi and di are the weights of the document, or the ith term with respect to the query and to the document. Notice that the weights with respect to the query and to the documents will be generally different in general, okay? You see that? Good. So this formula is in some sense agnostic with respect to the way in which I compute the weights. I have weights, and I want to compute the inner product. How am I going to compute these inner products? So when I write for every term, it means that I am taking this and I'm writing for every I, correct? What do I have to do for every I? For every I have to update the weight of the ith term with respect to the document I'm considering, okay? Actually, for each query term, comma, enter the posting list of the query. And then for every document, I am just considering this term, okay? So in the cycle, here the sum is with respect to I, here the fourth cycle is with respect to the document, okay, not with respect to I. So when I consider this for each, what I'm doing, I'm scanning all the documents, I mean, not all the documents that appear in the posting list, and I am just adding this term. That's what I'm doing, okay? That's it. When I'm finished, I have the following. I have the scores of the documents, and then I have the total length. What is length D? Well, it is just this. Okay? I have to divide by the length of the document. The length of the document is just the 2 norm of the document, nothing more. As you see here, I'm not dividing by this. So this is not really the cosine similarity. It's proportional to the cosine similarity. But as I told you, this is common for every document, so I don't need to consider it to the purpose of ranking. Okay? That's the algorithm. Simple. Notice that this is called, as an algorithm, this is called one term at a time algorithm, because the fourth cycle is over the terms. The outer fourth cycle is over the terms. So if you think of a real system, here you are picking one posting list after the other and updating the score for every document. Okay? So that's important. Because you have seen also that when you do Boolean retrieval, for example, sometimes you can do things in parallel, right? So you can try to do a parallel merge in which you advance along all the posting lists at the same time. That is not what we are doing here. That should be clear. So this is sequential with respect to the terms appear in the query. What else? Unless you have questions, I think I can jump to the next slide. No? I'm free to move? Okay. So, as I was telling you, you have many variants. Actually, people and normally you find them implemented in most packages, be they in Python or R, whatever, that implement Tf-Idf weighing. Okay, and you have a lot of them. You can use the standard one we were using, 1 plus log, or you can use strange things. Why are you using those? Because they have been proposed in some paper, I don't know, appeared at SIG-IR forum, in which they were proving that in certain collection you could achieve precision at K better than the standard way. Okay, and then someone else came and was showing that perhaps for longer documents this might actually prove better, and so on. And so you have a number of choices. Okay, if you go normally, if you have some package implementing these weighing schemes, they will tell you when they're performing more or less better. I mean, these are the type of things I don't want to remember. Whenever I need them, I look them up and check. Okay, just to be clear. But then comes the problem of saying which type of scheme you're using. And so there is a notation for saying what you're doing. It is the Tf-Idf notation. So essentially you say what you're doing for scoring the terms with respect to the document and with respect to the query. Okay, so Tf-Idf is a special case of this notation. You could have, for example, Tn. Let's see an example. No. What is that? Where was it? No. Well. LNC, for example, you take logarithmic. You take logarithmic Tf, no IDF, and then normalization. Okay, and then you take cosine similarity. Or you take logarithmic inverse document frequency, and you take cosine normalization, and so on. Okay, just did you go with this example? Huh? Yes or no? No? Yes or no? No. Okay. Then we take a look at the example. Try to make sense out of it. It is not terrible. Huh? So they give you some information. So you have a query, you have a document collection. Then you have a query. And actually you have 4 terms here. They will be thousands, but in our case, I guess you want to query. So you want to consider the score of document, let's say car insurance, auto insurance, with so a document containing those words, with respect to the query best car insurance. Okay. So first of all, the document car insurance, auto insurance. Is the position of the term insurance in the document important or not? No. It is the bag of words model. So we are just counting the number of times insurance appears, which is 2. Okay? 2, 1. So best is not appearing. So this is the row frequency vector corresponding to the document. And for the query, this is the row frequency vector. And now you can compute all you want using the scheme you want. For example, if you're using the row frequency counts for the documents and the logarithmic counts for the query, you will get for the different terms something different. Okay? Now, there is a question here which is interesting. If you see, look at this data. Can you come up with the number of documents in this collection? Yep. How many?
66,000.
Huh?
66,000.
66,000?
I just counted the DF.
Yeah, you had the document frequency, correct. And now, you take the inverse document frequency. Let's take this one. For me, it's easier. Huh? So this is df. So this denominator, look. Actually, df is 10,000, right? And it is 2. So it is 1 million, right? Okay? It's just an exercise. I just need a couple of minutes. So from this stuff, you do the math. I don't want to do it again here. I mean, it's really boring. But you just apply the formulas you have seen, and eventually you get normalized weights for the documents. So this is the vector representation of the document.
Of the query.
Huh?
Of the query.
Lo sta.
Of the query.
Sorry, of the query and of the document. Correct. Okay? Here. Then you take the inner product, and that's what you're left. Finished. It was an inner product. The lengths are unit, so you just say the inner product and you're done. Now, and then we are finished. I mean, at least I think this is where Professor Vitaletti finished more or less last time. So we have seen a number of ways, actually, the main way to rank documents, which corresponds to textual search engines. This is essentially what was done until the late 90s in many cases. Then people started to do something else. It doesn't mean that this stuff was killed. It is still there, actually. It provides a lot of useful information, but there are a couple of ingredients that are missing. The first ingredient is the following. Is all text equally important or not? If I give you a web page, the same word, can it be more or less important in the same document? What do you think? Huh? Yes? Why? The question is the following. I give you a web document intended in this case as a web page, HTML document, simple. And I give you one word appearing in the document. Can the same word be more or less important for the document?
Because it depends on the context.
On?
The context.
What do you mean, the content?
Based on the context of the meaning of the word.
Where it appears, you mean? Ah, sure. Your colleague is saying it depends on where the word appears. In an HTML document, actually, you have, it's semi-structured, right? So you have some areas defined by HTML fields. For example, you have a title. You can have, I don't know, an abstract, or then you can have a main body. You can have several fields, and depending, so you can have paragraphs with headlines. Depending on where the word appears, perhaps it is more important. For example, I don't know, if I have thrones, the word thrones appear in the title of the document, that provides a lot of information. I would not be surprised if it were discussing the last season of Game of Thrones, right? So, which we are waiting to see. Others is when it appears in the middle of the body, okay? So, this is one first issue we did not consider. Then there is another issue which I completely neglected so far, which is the fact, I mean, we have seen a document, we have been looking at documents. So we have considered the contents of the web pages without taking into consideration the way in which web pages are connected to each other, right? I mean, there is hyperlinks. That's important. So if I'm linking to your web page, I'm thinking that you're important for what I'm telling in my web page. Correct? You see that? Yeah, we have not considered this piece of information yet. So perhaps not all pages are equally important, because this is relevance. Huh? This tells you how much a page is relevant in terms of the text that appears in it for the query you asked. But it is not telling you that the page itself provides valuable information. It could be rubbish, actually. A lot of information in the web is junk. We know that. So relevance is not the same as quality. Can we add quality as well as part of relevance? That's the second question, okay? But let's say this was mostly the picture at the end of the 90s with, let's say, some structure. Let's say that if a word was appearing in the title of the web page, it would be more important. It would be weighed more, okay? This was taken into consideration, but not much more than this. And then you would get a page of results sorted in order of relevance, and then you would have to find your way through this huge amount of documents, trying to find out the more authoritative for the query you were asking. Okay? And that was complicated, because nowadays you look at the first page of results, actually the first 3-4 results. Yeah? There, you had to go to the, I don't know, first 50 or 60 pages of result before you find something interesting. Okay? Could happen. Okay, I'll give you further details of what you have done and so on. So that's finished. Now, what did I want to show you next? It was this, actually. Let's see. Should be this. No. What is this? This is wrong. Yes, dessert. Okay. So, is it my problem or the words are barely readable here? Is it my problem? I'm colorblind, so. You too. Okay, we are all. Then it is a problem. Okay. Yeah, this is not really important. I mean, apparently here the instructor made a mistake in previous lecture, so he wanted to correct himself, saying that actually that's the right way of proceeding. Yes, by the way you have defined weights. So essentially the weight is 0 if the word does not appear in the document. Fine. We take note. We take note of what the instructor of this course has written. Okay? So, I think we already did a recap, so we can skip this. And we already did this, and we did this now. So we'd like to do a number of things here, which is, I showed you one algorithm to compute cosine similarity. So in principle now, I'm not kidding, if we have a small document collection, we can set up an interface whereby we can compute cosine similarity with respect to a given query, and so we can look for the k most relevant documents for the query. Already now we can do that. And actually I think I have some exercise, some lab somewhere from last year which I'm going to show you. Not today, I think Thursday perhaps, on how we do this, just to compute cosine similarity. So in principle we already can do this. But now there is an issue. If you really want to build, let's say, an industrial search engine, a commercial one, you need to speed up things a little bit. Well, I mean, you may want to add further ingredients, but that's another story. What you want to do, first of all, is speed up your search engine. You want half a second tops to return an answer. You do not want 2 seconds. That's too much. Okay? So there is the issue of how you are essentially implementing the algorithm I showed you earlier in a fast way. efficiently. So, just to remind you, this was the algorithm we were considering. Huh? So, if you think about this algorithm a little bit. Now, assume that you have, I don't know, 1 billion documents. And your dictionary is, I don't know, 50,000 terms. Actually, it's bigger, but for a search engine. I mean, you know, if you consider a search engine, that is not a word of it in Italian, right? But you may find this in the search engine. Because in Italian, for example, that has a meaning. So in some announcement, you know? Yeah. So the vocabulary of a search engine is normally, in a given language, is normally much more expanded with respect to the standard vocabulary you associate to that language. You see what I mean? So vocabulary is large. Your document collection, let's say, is 1 billion documents. So this is going to be efficient. What can we do? Think of what we have to do. I give you a query. Think of what we have to do. I give you a query. Right? We have to look up the posting list of every term. Is this going to be fast? Why? I have to look up the posting list. So the head of the posting list. Is this fast or slow? That is fast. We have a dictionary, right? So you give me a term, I access the corresponding entry immediately. Yeah? I don't know, I have a hash function perhaps. I'll find the entry soon. That's not a problem. The problem is I have to scan the entire posting list, right? That's one first problem. The second problem is the following. I'm scanning one posting list at a time and not in parallel. The third problem is the following. I rank all the documents with respect to the posting list. You see that? What is the, you see here, line 10. This looks harmless. This is a poor instruction of pseudocode. This looks really harmless. Just give me the top K results, please. Like this. So, what is this at the end? This vector, scores D, equals scores D divided by length. So this vector at the end, is it a sorted vector or not? So there is the vector sorted or not? No. But I want the top K entries. How much is this? So 1 billion entries, let's say, okay? And I want the top K ones. Now the top K is normally, I don't know, 10. Let's say just to be safe, let's say 50. Huh? I mean, if you are one of those users that seam through the more than 50 pages, I really envy you. Huh? I normally stop at the first half of the first page very often, most of the time, right? So, of course, Google is not going to consider all the sorted vector. Come on, let's be serious. They care about, I don't know, 20, 30 top results. So K is a relatively small number, but your vector is not sorted.
It's super easy.
Huh?
It's linear. It's a linear.
Hey.
You don't need to sort
Well, yeah, linear. Is linear a lot or not? No? Let me write we can write in Python a for cycle over a billion elements, over a list of a billion elements. It's linear, but we are, you know, and this is not an array. I mean, this is actually documents. It means then you have to fetch, when you have found the documents, you have to dynamically build a search results page, right? So the results page you are not building before, because you don't know what is the top K documents for your query. You are building it on the fly. So on the fly you have to compute cosine similarity, blah, 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 run this algorithm, compute this. Once you have this, just the final step, find the top k elements by scanning linearly for k times a 1 billion vectors.
No,
How long is this going to? Right?
We don't need to do it k times. We can take the first k.
Fine. Yeah, you can. Of course, you can do more efficient than that. Even
if it's not sorted, you can take the first k.
Sure. Yeah. While you are computing the max, you can take the first k max. Yeah, there is k selection problem. It's you can do it efficiently, more or less linearly. Yes. How long is it going to take? Is it half a second? It's not. And anyway, computing the k, so computing the top k elements cannot be linear. If it were linear, you would compute the top n elements, which means you would be sorting in linear time, which is not possible. So actually we know that you need more time. Normally you will need at least k log n time, depending on the data structure you're using. Okay? I mean, there is some hope, but I just want to point your attention to the fact that this last step is not harmless. Okay? So here you have to be careful. Remember, you want those 0.5 seconds top to return a query, and including everything. Okay? Parsing your query, submitting the query, computing cosine similarities, everything taken, that has to be 0.5 seconds at most. And the work collection is expanding. So we need to call our engineers, so you, sit down and say, okay guys, we have to think of something. I mean, we are very good, we have set up the best algorithms, they are really fast, but so we have to scale. Okay, so what can we do? So actually, let's take a step back and let's try to be how should I say? Let's try to be practical. What does it mean to be practical? Well, let's think, what do we want to do? First of all, do we need a sorted vector? No. We are just interested in the first k, the top k elements, right? So it is not a sorting, it's something less. Second, do we need to really compute all coefficients? Exactly, no. We just want a ranking. And that is one of the reasons why we didn't take the query's weight, the query's length into consideration at all. It doesn't, it's the same for every document. But then, do we really need to compute the cosine similarity for all documents? I mean, do we really need? We just need the top k. Is there no way we can leverage this fact? So the fact that we are just interested in the big guys to compute less, to perform less than all cosine similarities. You see, because this is another bottleneck, right? So this is terrible. This is a terrible bottleneck. Huh? So you want to compute cosine similarity for all the documents. I mean, that's every time. Come on, let's try to do something else. We are not going to survive this. And then for every word, I have to do this to scan the posting list. So I have two ways here. Either I do not scan the entire posting list of all the terms, or that's another alternative, I kill some of the terms. But you can do that only sometimes, because very often the queries are already very short. What should you kill? I mean, I give you a query of 2 words, and you kill 1. I mean, you're killing the query. So very often you try to kill the posting list. So you try to compute, you try to not consider all the documents in the posting lists, okay? And in order to do that, you have to accept some, perhaps, degradation of your accuracy or performance or the quality of the answer you provide, okay? So, let's say, how can we speed up cosine computation? Actually, so it is a top K problem. Some people of you apparently have taken big data, so they know that actually with top K, perhaps there is a way to do things. yeah, an approximate way to do things. That's not, I mean, perhaps you are doing, but we do not have to go that far for answering queries in a search engine. Let's say that very often the queries are short, and we are going to take advantage of that. Another point is that perhaps we do not have to search the entire space of the documents for the query. Okay, perhaps there is some way we can proceed. We have seen this already. We don't normalize the query vector, just to be clear. I told you already the query vector is irrelevant. So the length of the query vector appears in every cosine product. It is the same for every cosine product. I'm just forgetting about it. Now, this is a bit more serious. Let's tackle the real problem. So here I'm assuming the following. I have run the entire algorithm, but now I have an unsorted vector, and I want to find the k top documents with respect to the sorting defined by the document scores. Is that clear? Huh? Oh. I mean, I'm putting integer values. Actually, the score is normally something between 0 and 1. Okay? Take the sum of the squares, divide it by it, and then you will get fractional values sum into 1. Now, this vector is unsorted. I want to find the top, say, 3 elements. Okay? I want to do this quick. Of course, I can sort the vector and then find the top k. We don't want to do that. What can we do? Go back with your minds to your second year of undergrad.
I take the element in the middle. I see the...
What's the name? What's its name? Huh? You are tortured with that stuff.
Binary search.
No, how can you do binary search here? This is unsorted. Something with priorities. There is a data structure that you use to heap. That's the word. Heap hop. That's it. That is something you can do. So why? Let's see why this is convenient. If you wanted to sort this array, this would cost you at least n log n, right? And the number of elements. You don't want to do that. 1 billion elements, come on. Let's be serious. For every query, no. No way. At best, what I can try to do is I build a heap. Why will I build a heap? Because if I'm building a heap over the elements, actually, so what is J here? Sure. So this is the vector in which you have one item for every document with non-zero cosine with a query, right? Of course, if you have 0 cosine with a query, it's not in the vector. So this will be a subset of the documents, all the documents that contain at least one term of the query, once. Now, for this document, let's assume they are J. What is the advantage with respect to sorting? That if you have a heap, you can heapify an array in linear time. That's the trick. You remember this? Yes or no? So the heapify of an array has a cost, a linear cost. So to heapify an array, you pay J. Let's say where J is the size of the array. Okay? This is already better than sorting the result array. And then, if you want the top k, you just build a maximal heap indexed with keys the values of the scores for the documents, and then you return the top k. removing one item from a heap has a cost logarithmic in the size of the heap, so you pay k log n. If you want to okay, there is some constant hidden here, but that's essentially the cost. That's the difference. If you apply sorting, that would be j log j. Here you pay j plus k log j. I mean, it's a lot of times. If it is a billion, the log of j could be something like 30. So j log j would be a lot, 1 billion times 32. Okay? This is instead is 1 billion plus, let's say, I don't know, 10 times 32. It's a lot less. I mean, is this going to be our golden bullet? I mean, still, come on, every time you build a heap over, no, we don't want to do that. It's an attempt. If it appears here, it's because someone has tried it. It can work with smaller collections, okay? You have 10,000 documents, you can try to do that. So, the point is that we are still computing cosine similarities for all pairs, for all documents with respect to the query. Can we try to avoid this idea? I mean, can we try to avoid computing cosine similarity between the query and all the documents in the collection? That is what we really want. And then, this is, you know, this is the borderline. This is the borderline with the theoreticians make their final considerations, and then the engineers enter the scene as practical people and say, okay, now we fix this. Okay? Yeah, you with your numbers. Okay, you have done your job. Now let us do ours. So what is the final consideration we can do? We can start philosophizing about this. So we say, well, in the end, what do we want to measure? Cosine similarity is measuring relevance of a document with respect to a query, right? What is relevance? I mean, what are we doing when we measure relevance? We are trying to actually think, to understand what that user there, whom I will never see in my life, had in her mind, right? I'm trying to read your minds. That is what I'm trying to do. I'm trying to measure your intent, what is called the intent behind the query, so what you had in mind when you submitted that query. And I'm trying to do this automatically and giving it a number. Come on, let's be serious. It's only a proxy. Very often it will work decently, but I will never be able to read your brains for the moment, at least. Okay? So, what does it mean? It means that intrinsically, cosine similarity comes with an error with respect to the truth, to the ground truth that I will never know. If you want to know what is the ground truth, you know what you do? You compute the ranking of your documents according to cosine similarity, then you provide the same documents to the user that submitted the query, and you ask her, please, could you run the documents for me? And then you check how your ranking compares with the ground truth. So it's a proxy. So if I make some more mistakes, who cares? So in the end, I have 1 billion documents. I have to give you 10 documents that are the good documents for your query. Maybe they're not the top ones with respect to cosine similarity, but perhaps the top K document, the top 10 documents with respect to cosine similarity are not your best choice. So, if the cosine similarity of the documents I give you is 0.8 instead that's 0.82, who cares? So essentially what I want to return is a good answer. So good documents to the query, possibly containing to a large extent the true top K documents. You see what I mean? For example, I will compute 50 potential results. Out of these, let's say 45 would really appear in the top 50 and 5 would not. It's not so bad. Okay? In that case, I will measure my precision at K with respect to, in this case, to the real cosine ordering, and I will say my precision at 5 is 45 divided by 50. 0.9 something. That's okay. I can live with it. Okay, that's the idea. So we want to give in the end a list of documents that is close to the top K in terms of cosine similarity. So remember, we are never considering what the user really has in her mind. We are just considering we want something that is close to the top K, which is defined by cosine similarity, okay? Which means we are still in a metric space, so we can measure our mistake. If I tell you which are the real top K documents, you will be able to measure the error you made. And that's it. At this point, I leave the scene, and the engineers come. They know everything about the search engine, the architecture of the search engine, so the nuts and bolts of the search engine, and so they will try to come up with some optimization. At that point, there is no theory to make. It's heuristics. We attempt to do something that works, something that is efficient and that performs well. We run a test. We provide a use case. We select a subset of the users, and we make an experiment on them without their knowing. We see whether or not they are happy. And that's it. If it works, it enters production. Okay? And the theorists go back to the mumbling. So, okay, let's try to formalize this a little bit. What do we want to know? Actually, we would like the following. Instead, we have a query, and we have all the sets, all the documents. We want to come up with a subset of the documents, which is called A there. It is called the set of contenders. Why term contenders? It means that they are documents among which the top K will be chosen. So instead of computing the top K with respect to the original entire document collection, you compute the top K with respect to A. Okay? For example, just to give you a number, instead of considering, I don't know, 1 billion documents, you consider 10 millions. Okay? So the idea is that the size of A should be, of course, larger than K, because otherwise you cannot come up with K results. But it should be orders of magnitude less than the document collection. Okay? So at the end, how do we speed up computation? How do we improve efficiency? We cheat. That's the reason. That's the answer. Okay? We are not really finding the super algorithm that is fixing everything. No, we are just cheating. We are trying to sneak our way through the results. You know, I give you good results, but perhaps not the top ones. So this is the idea. And this is a general scheme. So the only question to answer at this point is, how do I define A? There are several strategies to do this. Since we are now we are entering the realm of heuristics, we are also entering the realm of experimental empirical evidence. How do you measure the outcome, let's say the outcome of a strategy? You do a user study, that's it. You don't try theory, no equations about this. You test and see how it works in practice. And many of the details we are missing because they are secret business of search engines. I mean, there are user studies, but to do the user study, you need the users. I can do the study, but I have no users. They are both the users and the studies, and the people who can do the study. Yeah. So, okay. I'm going to stop in a couple of minutes. I just wanted to arrive at a point that makes sense. Let's put it this way. So, there is a number of heuristics I can choose from the most obvious one. Of course, you're just considering documents that contain at least one query term. And you know this. I mean, you can check whether the document contains, whether whether it appears in the, you can pre-check whether it appears in a posting list or not. Okay, only appears, not the weight, just check whether or not it appears. So, one thing I could do actually is to consider the following. Let's try to first reduce the number of posting lists I have to consider. In order to do this, I reduce the number of terms in the query that I'm going to consider. I already said that this is not really helping a lot because many queries are just few terms. But in case you had a long query, which sometimes happens, for example, when I copy-paste the title of a page, of a paper, because I want to look up the paper in the web, on Scholar, you know? I have a paper in some bibliography, I copy-paste the title plus a couple of the others, I paste it, and then I look it up. In this case, the query is pretty long. So perhaps you can apply the strategy. How can I decide which queries to eliminate? Well, for example, a sensible way of proceeding could be considering increasing, sorting them in order of decreasing IDF. So I mean the rarest terms perhaps should appear in the query because they provide a lot of information and the documents I'm going to retrieve are more likely to be relevant for the query. That's the first strategy. Then you can do the following, you can, you know what? I only consider documents that appear in many posting lists. So for each term you have a posting list, you just want to have documents that appear in many of the posting lists. Of course, this is not going to speed your computation when you compute cosine, but at some point the final vector will be shorter because many documents will have been removed. Many components will have been removed from the vector. Okay, so these are two decent strategies you can use. I mean, this can work to some extent, but this is not the final weapon. Yeah, and I mean, okay. An example. I guess you get it, right? I just want to consider documents that contain at least 3 out of the 4 terms in the query. Then you see which scores are computed for which document. For example, Anthony, so document, let's see, 3, nope. Document 3, no. Document 4, no. Yeah? You see the shaded docs, doc IDs are the ones corresponding to documents that will be considered. Now, this is a serious idea. Engineering. So since it's a serious idea, this is the point where we can make a break. So I'll see you in 15 minutes. Okay?